Hello and welcome to another power system analysis class. In the previous class, we started per unit systems. We solved some practice problems on that and some examples. Today, we will continue with three-phase. We already with this brief introduction to three-phase systems and three-phase transformers and their connections, different type of connections in three-phase transformers. Today we will continue three-phase transformers. Again, we finished three single-phase transformers for an ideal transformer and non-ideal transformer, and also per unit analysis. Today we'll start with three-phase transformers and non-ideal three-phase transformers, and how do we connect them. So there are four ways that we can connect three-phase transformers. We can connect them in the YY configuration. We can connect them in delta-delta. And we can also connect them in, I'm sorry, just Y delta and delta Y. Just give me 1 second. And the other type of connections are delta Y and Y delta. Now, YY and delta delta are completely different in analysis. Y delta and delta Y are the same, but they are just opposite of each other. And each of these configurations are used in a different application. And I'll explain how they are. Now, the first type of connection is called the YY connection. It's a magnetic coupling with an AN, AN, BN, BN, and CN, CN. So the primary winding is shown with the capital letters A, and the secondary is with the lowercase a. And a YY connection is exactly like a single-phase transformer. It's very easy, but it's just instead of having one set of windings, you have three. By the way, in the three-phase, you may show it separately, but we usually have a single core. And the single core usually looks like this. Next class, I will bring you one. The single core usually looks like this. They are connected to each other, but it has like three teeth. It's like a comb brush or something like that. And then you have each of these on one of these three phases, and then you have another three phase that are, but usually they are a single, use a single core because it's easier, it's cheaper to produce, and so on. Now, the YY connection, as mentioned, is like a single phase transformer. And a single phase transformer, the turn ratio V determines the primary and the secondary voltage ratio as well. So again, the same as a single phase, VAN to VAN, this is the primary, the capital one, and the secondary. It's going to be, the ratio is going to be equal to A, which is our turn ratio. In other words, it's N1 over N2. And it's the same for VAB and VAB and so on. And the current ratio is the opposite. It's 1 over A. Now, one benefit of a YY connection, do you remember what is the benefit of a Y connection three-phase system? Why do we prefer a Y connection, especially in transmission systems? Because in a Y connection, you don't need a neutral line. So instead of having 4 lines, when we balance it, we can only use 3. And that's a huge benefit of the system. That's the reason we like the YY transformers, because you get rid of the N connection. And it makes it much easier, and it's much simpler to actually work with it as well. Now, the previous picture showed an ideal transformer. Obviously, for a non-ideal transformer, we have copper loss, we have eddy current, we have magnetic flux and loss in the system. And all of those are exactly like a single phase transformer that we had, but now we just put each in each line, we put it in each branch of the system. And you can see we have RE, JXE, JXM, and so on. So we have three of those. For each phase, we would have one model, and we can show it like this. Now, to simplify the three-phase model, instead of showing all the three phases, we can only show one phase, and we can simplify it like this. And we can also, exactly like a single phase transformer, we can model it and solve this using a per unit system as well, and a per phase using the per unit system as well. Now, a per phase model analysis of a Y-Y connection is exactly the same as analysis of a single phase transformer. So if you're giving a three-phase Y connection, you solve it exactly like we solved for a single phase transformer. These Y-Y connections, transformers, are very common in transmission systems. And as mentioned, the key advantage of these systems is the ability to ground each side, and there is no phase shift to introduce. So instead, again, because it's a balanced system, we can neutralize, connect the neutral to the ground. It's easy to couple them. And in addition to that, there are no phase shifts in the system, which helps a lot, again, especially when you have reactive power and the power factor is not very good. So this would actually help to stabilize that and not make it worse. Now, let's solve a example for a three-phase Y to Y connection. I'm just going to give you these papers. It's because of attendance. We'll give you extra points when you solve them, but it's mainly, again, for the attendance. So the first example we have a Y-Y transformer, which has a turn ratio of A equal to N1 over N2, exactly like a single phase transformer, which is equal to 4. The primary line voltage is 138 kilovolts, and the secondary line current is 200 amps. First, we want to find the secondary line voltage, and we want to find the primary line current. Pretty simple, exactly like a single phase that we had. But this one is a three-phase. And the equation that you can use is the equation that we have here. VAN over VAN is A, VAB over VAB is A, and IA over IA is also 1 over A. If you wrote this down, I can go back to the question so you can. Did you write it down? Okay. So again, exactly like a single phase. Yes. Did you solve it? Yes. Do you need more time? No. Okay. So first thing to keep in mind is this is a line-to-line voltage, okay? And we want the secondary voltage and also line-to-line. So if this wasn't line to neutral, it's going to be a different story. So from the equation, we already know that VAB from the primary to VIAB of the secondary line to line is equal to A. And A is equal to 4, by the way. So therefore, the secondary line to line VAB is going to be 138 kilovolts divided by 4, which gives us 34.5 kilovolts. Now, if we wanted, this is the line to line voltage. If we wanted to find line to neutral voltage, you would divide it by square root of 3. Now, the line current, and by the way, the line current is going to be the same as the phase current and the star connection. So IA over IA is 1 over A. Therefore, IA would be equal to IA over A. Well, this is the primary, by the way, which is 200 divided by 4 gives us 50 amps. Right? Simple and easy. Did you write it down? Yes. Can I go to the next slide? Okay. Now for delta-delta connections, the magnetic coupling with AB and AB, and we have BC and BB, and also CA and CE. I'm sorry, that middle one is BC. And VAB over VAB, it's going to be the same. Again, we have 3 different coils or wiring wrapped in a single core, and it's basically like a 3-phase, 3 single phases. And again, VAB over VAB, or its primary over secondary, is going to be A. IAB over IAB is 1 over A. IA over IA is 1 over A, and so on. Now, the pair phase equivalent for a non-ideal transformer looks like this. Again, we add the different losses in the system, which are copper loss, magnetic loss, flux, and so on in the system. And what we get is 3 phases that are connected in a delta configuration, the same as a single phase, but now these are connected in delta configurations. Now, if we want to do a per phase model, Again, we can do it as a single phase, but the only difference is that the impedances are decreased by a factor of 3, meaning all the impedances, as you can see, for a delta connection is going to be the single phase divided by 3. So we have the resistance divided by 3, the impedance, the admittance, all of them are divided by 3. Now for a Y connection, we didn't change anything. It was exactly like a single phase. But for a delta connection, you must divide everything by a factor of 3. Now, key disadvantage is the delta-delta connections cannot be grounded, so therefore they are not commonly used. Again, a big disadvantage of a delta-delta connection is that they cannot be grounded, and therefore they are not commonly used in three-phase systems. And the other thing, when you want to model it, you have to divide all the impedances by 3. Now, let's solve a problem. We have a delta-delta transformer, and it has an A of 2. The primary line-to-line voltage is 24 kilovolts, and the secondary line current is 300 amps. We want to find the secondary line voltage and the primary line current. Again, I'll give you a few minutes to think on this, and then I would solve it. And by the way, delta-delta, we don't have phase shift and in the YY. But in delta Y and Y delta, we would have phase shift. And that's actually one advantage that sometimes it's used. It's going to be, again, here is the delta-delta equation. It's going to be the same as what we had for a single phase. Did you all solve it? Okay. Again, it's pretty easy. VAB for the secondary is going to be VAB of the primary divided by A, which is 24 divided by 2 gives us 12 kilovolts. And IA is going to be IA divided by A, which is 300 divided by 2 gives us 150 amps. So when you are solving for voltage and current and delta delta and YY connection, it's like exactly the same as a single phase transformer. But when you're modeling it, it's going to be different. And they don't have any phase shift. This is very important as well. Now, the next type of another type of three-phase transformer connections are the delta Y connections. There are magnetic coupling with V of AB, AN, and BC, BN, and CA, CN. So you can see it's a little different than the delta-delta connection. VAB is actually coupled magnetically with AN of the other side. CB is magnetically connected to CN of the other side. And AC, sorry, this is, yeah. And AC is, CA is connected to CN. I got this one wrong. CA is magnetically connected to CN. And CB is connected to BN. Now, since the line to line and the line to neutral voltages are different in the delta and Y connection, therefore we're going to have some differences from the YY connection and the delta-delta connection. So for the delta-Y connection, VI relations will look like this. Relationships will look like this. VAB over VAN would be equal to A, and VAB over A would be VAN. But VAB itself is going to be square root of 3 VAN with a degree of 30 degree. Now VAB, the second one, is the line-to-line voltage of the secondary. I can write it like this. VLL of the secondary is going to be square root of 3 V of AN of the secondary. But now here we have a 30 degree phase shift as well. Now hence VAB is square root of 3 VAB, which is the primary with a 30 degree over A, and VAN is square root of 3 VAN with a degree of 30 degrees over A. Now we have for the current, we get IAB over IAB is 1 over A. Therefore, IA is A, IAB. Again, this is the secondary, and I with a capital AB is the primary. Now, IA is going to be square root of 3 IAB with a degree of negative 30 degrees, and IAB is 1 over square root of 3 IA with a degree of 30 degrees. Again, the line-to-line current is 1 over square root of 3 of the line-to-neutral current. Now, IA would be equal to A, 1 over square root of 3, IA with a degree of 30 degree. So you can see it's completely different than what we had when we had delta connection and delta-delta or YY connection. And we also have the 30 degree phase shift as well. Now a delta Y connection per phase model will look like this. Again, for the primary side, we would divide all the impedances by 3. So we're going to have RE divided by 3, JXE divided by 3, and JXM divided by 3. And then what we have is the voltage is going to be square root of 3 over A with a degree of 30 degrees. And we have the final output. The connection introduces a 30 degree phase shift common for transmission, distribution, step down, since there is a neutral on the low voltage side. So this sometimes is used for the distribution side when the step down, we have a step down voltage even if A is equal to 1, there is a square root of 3 step down ratio. So even if we have a 1-to-1 ratio of transformer, we still have a square root of 3 step up ratio for the voltage. Now, a Y delta connection is the exact opposite of delta Y. The difference here is that we don't need to divide all the impedances by 3. It's like exactly when we had a Y model for a per phase model. And the other difference is we have a negative 30-degree phase shift here. So in a delta Y, we had a positive 30-degree. And in Y delta, we have a negative 30-degree. So keep this in mind. You may have this in your exam. And all the impedances are going to be the same as a single phase, the same that we did for a Y connection. Now, let's solve a problem. Example, we have a delta Y, not a Y delta, a delta Y transformer, which has a turn ratio of 1. If the delta sideline voltage is VAB of 13.8 kilovolts, again, this is a line-to-line voltage, we want to find the Y side line voltage magnitude. And go back to the equations if you want to take a look at the equations for the delta Y connection. And again, for Y delta, it's the exact opposite of this. Again, it's VAB is 13.8 and A is 1. Do you want me to go back to the equations? Or yes or no? Okay. Okay, did you solve it? Yes. Okay, what is the answer? Yes. Yes, okay. So VAN is VAB over A, and we know that VAB, or the secondary side, is going to be square root of 3 VAN. Since A is equal to 1, then VAB would be equal to square root of 3 times VAN, which is 13.8, gives us 23.9 kilovolts. Now, there's also a 30 degrees phase shift in the system as well. It's going 23.9 kilovolts. So we studied single-phase transformers, three-phase transformers, and their different configurations, which were delta delta, Y Y, Y delta, and delta Y. We also have other type of transformers as well. One type of transformer that is also used is called the load tap changing transformer. So the load tap changing transformer, or L2C, they have a tap ratio that can be varied to regulate bus voltages. The typical range of variation is positive, negative 10% from the nominal values. Usually it has 33 discrete steps, or which each step is 0.0625% per step. And because this is a mechanical process, a mechanical system, and the tap changing is mechanical, they usually have a 30-second dead band to avoid repeated changes. And unbalanced tap position can cause circulating volt amp reactives. Now, this graph in this picture shows a load tap changing transformer, and you can see that we have the low voltage side and the high voltage side, and you can physically change which part of the transformer we can make the connection to. Therefore, we can change the number of winding ratios. Okay, we can't change it by that much. Usually it's just 10%. And the reason we do it for 10% is just to match the load with the generation and to be able to match the voltage. Since, as you know, when you have a load connected, it suddenly drops the voltage, and to compensate that, you can alter this to be able to compensate for that voltage. But you don't need to do a huge swing. Usually it's just 10%. So you go from the load side, the low voltage, from let's say 120 volts to 100 volts. Immediately you want to increase the supply side to be able to increase that voltage back to 120 volts. And usually, as mentioned, because this is a mechanical process, you have a little bit of a delay. And here you can see the connections, the coolants going inside of them, and the mechanical steps that is required to change the ratio, tap ratio. Now, another thing to keep in mind, this is usually done automatically, and it's a three-phase system. So you have a three-phase Y connection. So you do it for each phase. So you're doing it for three phase. Usually if it's a balanced system, it's a single phase and you're changing it. Some systems are able to individually connect those transformers. Now, again, it has 33 steps. I'm sorry. Each step is 0.0625%, and it's a 10% change. It does a 10% change. But this system have some disadvantages because it's a closed circular loop. It may cause volt amp reactive, or we call it circulating volt amp reactive, or VARs. These are loops of reactive power that flow back and forth between two or more pieces of equipment, most often parallel transformers whose tap setting or impedance don't match. Because the loop is closed, the reactive power never reaches a load. It simply circulates through the iron and copper of the connected device. Now, this obviously creates power loss in the system. So it's because it's a volt amp reactive. It's not real power, it's reactive power. And this reactive power is wasted through the system via heat. So it may cause some damage. So we have to be able to counter that. Then we can do like power, capacitive banks and so on to be able to compensate for that. Now, another type of transformer is called a phase shifting transformer. Now, these are very important and useful systems. These type of transformers are used to control the phase angle across transformer. We know that in a three-phase system, in a AC system, power factor is very important. We want the power factor to be close to 1. And we want the apparent power to be very close to the real power. We want to reduce the reactive power as much as possible. Now, one way to do that is for power factor correction do you remember what is the power factor correction method? A capacitive bank. Another way to do that, and that is usually put on the load side. We usually put it directly on the motor. It has a huge effect on the motors when you have a winding. Sometimes, but you need to have phase shift. In a large scale, we can use a phase shifting transformer. These are also called the phase angle regulators, or PARs, or quadrature booster transformers. And since power flow through the transformer depends upon the phase angle, this allows the transformer to regulate the power flow through the transformer. Phase shifters can be used to prevent inadvertent loop flow and to prevent line overloads. And you can see that how it's connected. You have a shunt transformer, which is connected, and the ratio is usually 1:1. And you saw that we have in a delta Y or Y delta connection, we have a phase shift. So we can use this type of transformer to be able to compensate for that. And we also have the series transformer. So we have a parallel and series transformer that we can use for phase shift. Now, this works when you have a fixed phase shift and you want to correct that. But when you have a changing phase shift, like what you have in motor, this doesn't work properly. So you need a capacitive bank for that to be able to compensate for that power factor, because power is going up and down and you have different phase shifts in those systems. Now, this example shows a phase shifter graph in a real-world transmission system. We have on the left, we have a 500 megawatt, 164 megavolt amp reactive generator. And on the right side, you have the load, which is a 500 megawatt, but now it's a 100 megavolt amp reactive. So, and in the middle, we see the transmission. And you can see that the power that is injected to bus 1 connected between those two is 283.9 megawatts, but 39 megavolt amp reactive. And on the other side, we have 283.9 with 6.2 megavolt amp reactive. So we reduce that from 39 to 6.2. And then we have the phase shifting transformer. We have 216 megawatts, 125 megavolt amp reactive. And then we can adjust that. We reduce the 125 to 93.8 megavolt amp reactive. So the phase shift actually works by shifting the phase and to some degree correcting the power factor. But again, it has its own limitation, but it's very good for high power, high voltage systems. Now, another type of transformer that I think you already saw when you had measurement instrumentation with me is called the auto transformer. And I'll bring one next week so you can look at it. It usually has a knob on it that you can move. It's like a linear, I don't know if you've seen those linear potentiometers, the big ones that you can move a knob and you can adjust the resistance. It's something exact like that. You have a knob that you move and it has like a needle, a commutator that moves along, and you can connect it to different part of the secondary winding. You can see you can move it through the secondary side, and therefore you can adjust the output voltage. It's good if you want to reduce, let's say, 300 volts to 200 volts, 100 volts, or 300 volts up to 600 volts, 3 times. But it's very dangerous and not will work if you have a very large A, meaning a very large ratio, and you want to reduce like 10,000 volts to 40 volts. The reason is that an auto transformer is both magnetically and electrically connected. So you can see that the connection between the input and output is both magnetically and also electrically, meaning the current can't pass through it. And the result is lower cost, smaller size, and weight. But the key disadvantage of the system is if something goes wrong, the high voltage would, and if you have a large A and you're going 10,000 volts, let's say to 100 volts, that is directly going to connect to the load. You don't want the low voltage side to be 10,000 volts or something like that. It's going to have devastating effects. So it works in very small incremental, changes. If you want to have a motor that, one good example that these are being used is Japanese electrical devices. They usually run on, let's say, European. They usually run on 220 volts, or Asian countries, most of them are 220. But Japan and US are 20 volts. So if you want to take your electronic or electrical device like a fridge and you want to use it in Europe, auto transformer is a good option because you can use it to adjust and increase the 120 volts, let's say, to 220 volts. That works perfectly fine. So you have some limitations because frequency here is 60 hertz, over there is 50 hertz. The system still would work, but if it's a fridge, for example, and you have a compressor, you're going to have that knocking on it. It's going to last much less than if it's designed for 50 hertz, for example. But other electrical devices, you won't have any problem, like a dryer. So for small changes, auto transformer works perfectly fine. Another example that you're going to see this in lab, especially, is when you are doing different tests, like the short circuit and open circuit tests on a transformer. For example, in a short circuit test, we want to start with very low voltage, so you can use a auto transformer to start with a very low voltage, AC voltage that you want to get. And you can easily, adjust that voltage and control that voltage. It's very good for low voltage applications, but it's not good for high voltage applications. Okay, that's it for today's class. Please let me know if you have any questions. And I'll post another set of homework this week, and you would have 10 days to complete it. Thank you so much.